Okay, in this video, we're going to cover VSEPR theory, which is a theory or model for predicting the shapes of molecules, or what we call the geometries. And what's important to understand is how to use this chart. This is an information page kind of thing that you can use. And we'll go over the two geometry types, which are electronic geometry and molecular geometry. So I won't spend too much time lecturing on this because you have lecture videos for that. But the electronic geometry is just dependent on the regions of electron density. So basically, these here, in other words, 2 regions would always go with linear, 3 trigonoplanar, 4, as you can see, these are directly tied into that, right? And then the molecular geometry, which is normally the thing that we are referring to if we just say geometry, this is the position of the atoms only. That would be the take home with the when we say molecular, we're talking about just the atoms and not the lone pairs. So not lone pairs. Okay. There's a little picture under the schematic column of what that would look like. If you can get your hands on a little chemical model kit, it's even better because you can actually see it in 3 dimensions and kind of hold it in your hands. But these pictures are meant to represent them, and then the bond angles are going to kind of show you the angle between those bonds in those pictures. Okay, and this is using the ax notation, which would be kind of a more simple way to start to kind of line them up and figure out what we're dealing with. So let's jump into one where we are looking at the geometries of carbon tetrachloride, and you'll want to draw the Lewis structure first. So I'll just kind of draw that down here. Again, make sure you can do these on your own. It's going to be like the blueprint. This structure is the blueprint we're starting with. You want to make sure that that is correct, obviously. When we do these, we're only looking at the central atom. So we're going to disregard all the lone pairs around the chlorines. We would want to make sure that they're there just so that we know we drew the correct structure with the number of bonds and octets and all that. But we're just basically focusing on the carbon. So when we look at the carbon, that's where we use the ax notation. So A is kind of meant to represent the carbon. X is the number of atoms bonded. So that would be 4. And E would be the lone pairs, which would be 0 because there's no lone pairs on carbon, right? So this is kind of the number of atoms attached to the carbon. This is the number of lone pairs on the carbon. Okay, so then again, we can kind of go here. You could find, oh, there's that's that. The geometry is going to be the electron geometry and the molecular geometry are all going to be tetrahedral. So, all right, electron geometry, tetrahedral, and molecular geometry, tetrahedral. And bond angles would be 109.5. So that angle just goes with tetrahedral. Okay. So that one's not too bad. And H2S, we would have a structure that would look like similar to water, just with sulfur in the center instead of oxygen. And so we have 2 atoms bonded to sulfur, and also 2 lone pairs, right? So we're counting kind of this bond as the X2, and then 2 lone pairs there. So what we're going to have for the electron geometry is tetrahedral. So by the way, if you add up the X plus E, that adds up to 4, right? And that's going to go with tetrahedral. So when you look at these, you start to kind of maybe put things together here. In the chart, anything where the X and the E adds up to 4 would be, again, this for going with tetrahedral for electron regions. And so when we have AX2E2, which we have in this case, the electron geometry is tetrahedral, but the molecular geometry is bent. And this is a picture of it, and the bond angles are less than 1 and 1.5. So I'm going to have molecular geometry being bent with less than, it actually says less than, because of the 2 lone pairs. So the difference between tetrahedral electron shape with 1 lone pair, so you get a little bit less of an angle, and with 2 lone pairs you get even less. So kind of that would be good to remember with these two. What that means is basically more lone pairs, smaller angle. And that's one of the keys of this theory, is that the lone pairs repel electrons more than bonds do. So the electrons in the lone pairs are pushing down on the bonds more than vice versa. So really, these two balloons of lone pairs are exerting kind of more repulsive force on these bonds, and that causes this angle to kind of shrink even smaller than it would ideally be if it was just a tetrahedral angle. Okay, that I think would be an important point to remember. All right, CH2F2. So for the Lewis structure, you can kind of draw it whatever way you want, and we'll get into this more with the polarity video, but put the hydrogens and fluorines wherever you want, as long as you have single bonds and lone pairs around the fluorines. That's everything's happy here. It's got octets for these. Hydrogens, of course, just have 1 bond. The notation is going to be like the first one we did, where on the carbon we don't have any lone pairs. We just have 4 atoms bonded to it. So the electron geometry and the molecular geometry will be, again, tetrahedral. And the bond angles will be exactly ideal for tetrahedral, 1 and 9.5. All right. For this one, we're going to have 2 hydrogens and oxygen. And when you do this, you'll find that you need a double bond here with the oxygen and then 2 lone pairs. Okay, so this brings up an important point, in that when you're counting the number of atoms bonded to carbon, it's just going to be 3. Because we count the atoms bonded. So a double bond counts as just one kind of bonded position. So you basically count double and triple bonds as just a bond in this notation. And the electron geometry, again, this is going to be kind of 3. That's going to go with trigonal planar. That's the basic electron geometry for having 3 regions around a central atom. And since there's no lone pairs, this is the same. So again, there's no lone pairs, the electron and the molecular geometry are the same, and the angle is 120, right? So kind of a better way to actually depict this would be all of these atoms, carbon, O, carbon, hydrogen, these bonds here are all 120 degrees apart, right? So it's symmetric in that way, in terms of the bond angles. So that might be kind of weird, but the double bond doesn't really repel any more than a single bond. So that's just not too intuitive, but this is part of the theory, and it works pretty well. It's actually pretty true to nature. Okay, so xenon difluoride is a good one to go over, because when we draw the structure, I believe there are 26, kind of doing this from memory, 8 plus 14, sorry, 22 electrons. So if we did this, it'd be 20. And we need to use 22 valence electrons. So what we do is we put the extra lone pair on xenon. So that's kind of a good little trick here. If you have to expand the octet, you always do it on the central atom. And so you're going to have an expanded octet on xenon, which is fine. It's big enough to accommodate that. So for the xenon, we have 2 atoms bonded and 3 lone pairs, right? So this is the 2 bonded atoms and then 3 lone pairs. That's how we get these numbers. So the electron geometry, when we have 5 total regions, that's called trigonal bipyramidal. And the molecular geometry is different because we have lone pairs on the central atom. Let's find our chart here. Okay, so we have, again, 5 total bond or electron regions with, that's, again, the 5 goes here, trigonal bipyramidal. And the molecular geometry is linear. So we have a 180-degree bond angle, which makes sense if it's a linear structure. And so we would have this molecule, we would call it linear, and it would be like basically how I drew it. So the fluorine, xenon, fluorine, that's those all 3 atoms are in a line. We get a 180-degree bond angle. Okay, as opposed to something where we had like this, and then we had the 3 lone pairs like that. So in the actual, like the Lewis structure, it's fine. But again, in the actual 3-dimensional shape of it, it's not going to be bent or something like that. It's going to be a linear. Okay, which again will be important for things like polarity. Sulfur tetrabromide, similar in that when you draw the structure, you're going to, if you do the octet rule, that would be 32 electrons, but you have to use 34 in this case. If we add up the valence electrons. So again, you'd have 32 if you did octets. You're going to have to put an extra, put a pair of electrons on sulfur to accommodate 34 electrons. So for sulfur, we have 4 bonded and 1 lone pair. So again, we get a total of 5 regions, which is trigonal bipyramidal. And the molecular shape, just the atoms, is what we're going to call a seesaw. So again, if you can consult your chart, we have X4, E1 being seesaw, and these are the angles. So they list 3 of them here because kind of it depends on where exactly you're looking in the molecule. I can kind of draw that down here. So what it would be is essentially you have a lone pair kind of like sticking out on one side, and then pretty much up and down ideally would be the two of the bromines, and then this dashed line means going into the page and the wedge means coming out at you. So it's a 3-dimensionality that's being shown, right? This bromine's coming out of the screen towards you. This dash is going into the screen. So here again, you can maybe look in your book for better pictures, maybe in your lecture slides as well. But the angles that would ideally be present, so between these would be a 120, but again, because of the lone pair, we're going to get a little bit less than that. You would have an angle between these two that would be ideally 90, but again, because of the lone pair, it's going to kind of squash them, right? This also would be a little bit less than 90. The 180 is weird, but it comes from the fact that if you measure like this angle to this angle, that would be 180 ideally, but because this, again, this lone pair is kind of pushing these away, this actually expands. So these bromines, they're kind of pushed to the right. So you get, so again, it just kind of depends on what two bonds you're measuring. That's why it looks maybe weird why some of them are less than and some of them are greater than, but not too big of a deal. I don't think it's going to be too big of an issue. If you have that chart, obviously you can refer to that thing. And lastly, this one is pretty easy because we have 6 chlorines, and if we add up all the electrons, we do the dots all around, we actually would have used up them all, which would be, I believe, 48. We have 6 plus 42, 48. This is 48 electrons. And 48 are shown. So we have X, 6 atoms bonded to selenium, no lone pairs on selenium. The electron geometry and the molecular geometry will be the same, which will be octahedral. So that's what goes with that 6 number, is this geometry called octahedral, which looks kind of the way I've drawn. Sometimes you'll see this more three-dimensionally with 2 wedges and then 2 kind of dashes going away. So that would be maybe, again, a more three-dimensional way to try to picture this octahedral shape. All the angles are 90. So it's very like symmetric in that way. These are all orthogonal kind of bonds. That's pretty much it. And again, just kind of practice and make sure you get the Lewis structures drawn correctly. And let me know by email, or otherwise if you have any questions. And good luck with the studying.